Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting far below the waves, down into a realm of total darkness that covers most of our planet, yet remains largely unexplored. The ocean floor is not a flat and empty plain. It is a landscape of mountains larger than any on land, trenches deeper than the tallest peaks, and valleys where new Earth is still being formed. It is a place of restless movement, immense pressure, and astonishing resilience. Beneath miles of water, complex ecosystems thrive without sunlight. Vast ridges stretch across the globe, ancient sediments settle into layers, and for billions of years, hidden forces have been quietly reshaping entire continents. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, simply settle in. Let your breathing slow and allow your shoulders to soften. And as the day begins to gently fade away, join me as we explore the deep foundations of our planet together. Let's begin. The ocean floor covers more of Earth than all continents combined. If you could drain the oceans, you would find that land is the exception, not the rule. Most of our planet's solid surface lies underwater, stretching across immense basins that link every shore. That hidden terrain shapes how heat moves through the world ocean, which in turn influences weather patterns above it. It also sets the stage for where nutrients circulate, where fisheries begin, and where carbon can be stored for very long spans of time. Entire regions of this sea floor sit in darkness so complete that day and night never arrive. And because it is so vast, even small changes down there can matter at planetary scale. When you picture Earth, it helps to imagine a water world with continents as scattered highlands. Earth's longest mountain chain runs underwater, called the mid-ocean ridge. There is a mountain system that wraps around the globe like stitching on a baseball, and almost all of it is underwater. Its peaks and valleys rise from the deep in a continuous band that threads through multiple oceans, often higher than nearby seafloor by a mile or more. In places, the ridge is broad and rounded, and in others it is split by long cracks and steep walls. Along its crest, volcanic rock constantly builds new topography, then cools and slowly sinks as it ages. The ridge also acts like a giant obstacle course for deep currents, redirecting them through passes and gaps. When researchers trace its path on maps, it looks like a living seam, marking where the planet is actively renewing itself beneath the waves. New sea floor is born where plates pull apart, at spreading centers. In certain places, the crust is stretched until it thins and opens, and hot rock from below rises to fill the space. When that melt meets seawater, it cools into fresh basalt, creating a new strip of ocean crust. Then the process repeats, again and again, pushing all the seafloor outward on both sides, like a slow-moving walkway. Over time, this makes a clear age pattern across whole ocean basins, with the youngest rock near the birth zone and older rock farther away. It is creation, with a steady rhythm, not a single event. You can imagine the seafloor being quietly assembled in long bands, then carried away to live out a geological life story, inch by inch, through the dark. Some trenches plunge deeper than the height of Mount Everest. The deepest parts of the ocean are not wide plains. They are narrow scars where the planet bends downward. These trenches are long, curved valleys, with walls that can be steeper than many land mountainsides. They form at the edges of moving plates, where one slab of Earth begins to descend. In the deepest zones, the water above is so tall that it could swallow the highest peak on land and still have room to spare. Exploring them is difficult, and every descent is like entering another world with extreme cold and complete darkness. Yet these trenches are not dead ends. They are active places where sediments collect, where rock is squeezed and fractured, and where the deep earth and the ocean meet in a slow, relentless embrace. Underwater volcanoes build seamounts that may never break the surface. Many of the ocean's mountains never become islands, even after erupting again and again. They rise from the deep like solitary giants, built by lava flows that pile up over long spans of time. Some seamounts grow tall enough to steer currents, which can concentrate food and attract life, turning a rocky peak into an underwater neighborhood. Others remain remote and rarely visited, which is why new ones are still being discovered during mapping surveys. Their slopes can be coated in slow-growing corals and sponges, or cut by landslides that send debris downslope into the abyss. And because each seamount records a particular volcanic history, the rocks can reveal where melting occurred in the mantle and how magma changed on its way up. It is volcanic architecture on a scale that feels mythical, hidden under miles of water. The deepest seafloor pressure can crush steel, yet life still thrives. At great depth, the weight of water becomes a force that reshapes what living tissue can be. Pressure there is not a sensation, it is an invisible squeeze from every direction, pressing into cells and proteins. For many materials, it is simply too much. But some organisms have found ways to make the squeeze feel ordinary. Their membranes stay flexible instead of brittle. Their enzymes keep working when pressure would normally twist them out of shape. Their chemistry includes molecules that help proteins hold their form, like tiny supports inside a crowded room. Food can be scarce, so many deep dwellers conserve energy and weight. The surprising part is not only that life survives, it is that it can be active, feeding, growing, and reproducing in conditions that seem built to forbid it. Most of the sea floor is mapped indirectly, not seen by human eyes. When people imagine exploration, they picture headlights cutting through darkness and cameras capturing crisp views. Down on the ocean floor, that kind of seeing is rare. The deep ocean is vast, and direct visits cover only tiny patches at a time. So our understanding often comes from carefully gathered hints, assembled into maps like a giant puzzle. Research ships trace long paths across the sea, collecting measurements that suggest the shape of what lies below. Satellites help by detecting subtle changes in the ocean surface that can reflect hidden features beneath. Still, large areas remain known only in broad strokes, more like sketches than portraits. This means new discoveries can be surprisingly close to familiar coasts, simply because no one has taken a close look yet. In a modern world, the seafloor still holds blank spaces. The ocean floor stores clues to past climates in layered mud cores. On the deep seafloor, sediments settle in quiet layers, and those layers can behave like a long memory. When scientists extract a core, they pull up a vertical timeline, with the youngest material near the top and older material stacked below. Each layer can carry a signature of the world above it, from tiny shells to dust carried by ancient winds. Some layers hint at colder oceans, others at warmer ones. Changes in chemistry can suggest shifts in ice on land, rainfall patterns, or currents that once flowed differently. Even rare events can leave a mark, like a sudden pulse of material arriving from far away. What makes this so captivating is the patience of it all. The ocean floor does not rush. It keeps recording, grain by grain, as the planet cycles through ages of change. Many ocean plains are flatter than deserts, built from slow-falling sediment. Far from coasts and mountains, the seafloor can become astonishingly level. These abyssal plains are the deep ocean's wide, open expanses, where the drama of ridges and trenches gives way to quiet geometry. Their smoothness is not an accident. It comes from a steady rain of tiny particles that drift down from the waters above, settling grain by grain over very long spans of time. Layer after layer, the seafloor is softened and evened out, like a landscape being gently blanketed. The result can be a plain so flat that small changes in height matter, and a single low rise can stand out like a hill on a frozen lake. These plains remind you that the deep ocean is not only wild, it can also be patiently precise. The seafloor quietly drives plate tectonics, reshaping continents over deep time. The ground beneath the oceans is not a passive basement for water. It is one of the main engines of change on Earth. As plates move, they carry continents like passengers, nudging them together or pulling them apart. Where plates converge, rock can descend into the mantle, and that sinking motion can tug the rest of the plate along, like a heavy anchor. This movement helps explain why mountain ranges rise on land, why volcanic arcs form near certain coasts, and why earthquakes cluster along particular boundaries. It also shapes the outlines of ocean basins themselves, which can open, widen, and eventually vanish. The timescales are immense, yet the effects are everywhere, in the placement of islands, the fit of coastlines, and the location of deep ocean features. The seafloor is not scenery. It is the stage machinery of the planet. Slow, spreading ridges can split into deep valleys called rift zones. When seafloor spreads more slowly, the crust does not arrive as smoothly, and the ridge crest can open into a dramatic central valley. Instead of a rounded seam, you can get a long, rugged trench at the top of an undersea mountain range, with steep walls, broken blocks, and faults that step down like staircases. This valley forms because the crust is pulled apart faster than molten rock can reliably fill every gap. The surface breaks, drops, and stretches, making a landscape that looks torn and raw. In those places, the seafloor can expose rocks that were once deeper inside the crust, offering scientists an unusual peek at how oceanic crust is assembled. It is also a setting for strange habitats, because cracks and faults can guide seawater deep into warm rock, then return it, altered, carrying heat and minerals back into the ocean. Flat-topped guyot reveal ancient islands that sank and eroded. A guyot is a mountain with a shaved-off summit, like an island that lost its crown. The flat top tells a story that begins at the sea surface, where waves and weather can grind rock down to a broad platform. Then, over time, the weight of the volcano and the cooling of the crust below can cause the whole structure to sink, carrying that flattened summit into the deep. It is a haunting kind of evidence, because it means some underwater mountains were once places where sunlight reached, where reefs could grow, and where coastlines may have formed. Now those same tops can sit far below the reach of waves, preserved like a fossil shoreline. Scientists use guyots to reconstruct past sea levels and plate motion, since a chain of them can mark a long journey across the ocean, one sinking island at a time. Subduction zones recycle seafloor back into the mantle like a conveyor. At certain ocean margins, the seafloor does not last forever. It bends, cracks, and then slides downward into the deep earth, carrying a cargo of rock and sediment with it. As it descends, pressure and heat rise, and materials that were once on the seafloor begin to change, releasing fluids that can trigger melting higher up. That melting can feed volcanoes on nearby islands or along continental edges, linking the deep ocean floor to fiery peaks on land. Meanwhile, sediments that erode the plate can be scraped off and piled into thick wedges, creating rumpled zones that can eventually rise above sea level. This recycling is one reason ocean crust stays relatively young compared with continents. It is also a reminder that the ocean floor is not an ending. In many places, it is a doorway back into the planet, where old ground is transformed into new possibilities. Great earthquakes often begin where one plate slides beneath another. Where plates meet at subduction zones, the contact is not smoothly gliding like polished ice. Portions can lock together, building strain for years or centuries as the plates keep trying to move. Then, when the locked area finally breaks free, the seafloor can lurch in an instant, releasing enormous energy. That sudden motion can ripple across the ocean as a tsunami, even when the shaking is far offshore. The frightening part is how silent the buildup can be, and how fast the release happens once the fault gives way. Scientists study these zones with seafloor instruments that listen for tiny quakes, measure slow deformation, and track changes over time, because each clue helps explain how stress accumulates. These earthquakes are not random tantrums. They are the snap of a loaded system, driven by steady plate motion that never truly stops, even when the surface seems calm. Magnetic stripes on basalt record ancient flips of Earth's magnetic field. Long before anyone could easily visit the deep, ships began noticing strange patterns in the ocean's magnetism. Instruments would pass over the same broad regions and register alternating bands, as if the seafloor carried a hidden barcode. The reason is both simple and astonishing. When volcanic rock cools, iron-bearing minerals inside it can lock in a magnetic direction, like tiny compass needles frozen in place. Over Earth's history, the magnetic field has reversed many times, and each reversal leaves a new band with the opposite orientation. So the seafloor becomes a record of flips that happened long before humans existed. Once scientists realized what those stripes meant, the ocean basins turned into a readable archive. It was as if the planet had been quietly writing its own history in stone, then waiting for us to learn the language. The East Pacific Rise spreads fast enough to outpace a fingernail's growth. Along this ridge in the Pacific, the planet is opening up at a surprising pace, and that speed changes everything about the seafloor nearby. Fresh crust forms, then is carried away quickly, so the hot, young seafloor stays relatively smooth and elevated before it has much time to cool and sag. That helps explain why the ridge crest can look broad rather than deeply scarred. It is also one reason scientists love studying it, because the recording tape of new crust moves along briskly and patterns become easier to trace across the basin. Even the chemistry of the rocks can reflect that rapid turnover, with magma delivered more steadily. It is a reminder that Earth can build new ground with a speed that feels almost human, even though the story it tells is planetary. Transform faults slice the seafloor sideways, linking ridge segments together. Not every plate boundary is a head-on collision or a clean separation. In some places, plates slide past each other, and the ridge crest is offset like a zipper that has been tugged sideways. These transform faults can create long, linear scars, with cliffs and troughs that mark repeated sideways motion over immense spans of time. Along them, earthquakes can be frequent, because grinding rock resists movement until it suddenly slips. Transform faults also shape the layout of the mid-ocean ridges, breaking a single ridge into segments that step left or right, then reconnect. This segmented pattern helps scientists understand how the crust is built in pieces, rather than as one continuous strip. It also creates varied habitats, since the rugged topography can channel currents and expose fresh rock. The result is a seafloor that looks engineered, with straight lines and sharp turns carved by the simple act of sliding. Fracture zones can run for thousands of miles across abyssal plains. If you look at detailed maps of the seafloor, you can find long, faint ridges and troughs that stretch like quiet highways across the deep. These are fracture zones, and they often begin near transform faults at ridges, then continue far into older seafloor. They are not always active faults today, yet their topography persists, because crust of different ages cools and sinks at different rates on either side, leaving a step in the seafloor. Over time, that step can steer deep currents, influence where sediments gather, and create subtle boundaries that matter to life that lives close to the bottom. A fracture zone can cross an entire ocean basin, linking distant regions with a single geological line. It is a beautiful example of how past motion leaves lasting traces, like a crease in fabric that remains long after the fold is gone. Some seafloor rocks are made of pillow lava, shaped by rapid cooling. When lava erupts underwater, it does not flow the way it does on land. The outer surface chills almost instantly, forming a thin, glassy skin that traps the molten interior. Pressure builds, the skin cracks, and a new bulge pushes out, swelling into another rounded lobe. Over and over, the eruption produces a stack of bulbous forms that resemble a pile of cushions. This shape is more than a curiosity. It is a signature that tells geologists the lava met water directly, which helps them interpret ancient rock sequences that are now lifted onto land. It also creates a maze of cracks and spaces where seawater can circulate, altering the rock and delivering chemicals that later feed deep ecosystems. Pillow lava is evidence of the ocean's power to sculpt molten stone in seconds, turning fire into rounded shapes that look almost soft, even though they are solid rock. Hydrothermal vents release mineral-rich fluids heated by magma below. In some parts of the seafloor, seawater seeps down into cracks, travels through hot rock, and returns transformed. It comes back loaded with dissolved metals and chemicals, and when it meets cold seawater again, minerals precipitate like smoke made of stone. These vent systems can create chimneys, shimmering plumes, and seafloor patches that look newly painted in bright minerals. They also create habitats that feel almost impossible, because the energy source is not sunlight, it is chemistry. Microbes use compounds in the vent fluids to build food, and larger animals gather around that invisible meal. What makes vents so compelling is how they connect worlds. The ocean becomes part of the crust's plumbing, and the crust becomes part of the ocean's chemistry. It is a circulation that can change seawater, build mineral deposits, and support life in places where darkness would otherwise seem complete. Black smoker chimneys can grow quickly, then collapse like brittle towers. Black smokers are built in real time, not over ages. Superheated fluid rises and meets near freezing seawater, and minerals drop out of solution like instant masonry. A chimney starts as a rough ring, then stretches upward as new layers harden along the rim. Inside, the flow stays hot enough to keep feeding the structure, and the plume looks dark because of fine mineral particles. The strange part is how temporary these towers can be. As chemistry shifts, the plumbing can clog, redirect, or weaken. Pieces crack, the stack tilts, and whole sections can tumble, scattering fresh mineral rubble across the seafloor. That collapse does not end the story. It can open new pathways, spark new growth, and rearrange the vent neighborhood like a sudden storm. Except the storm is made of stone. White smoke vents form when different minerals precipitate from cooler fluids. Not every vent roars out at extreme temperatures. Some are cooler, and that changes what the water carries and what it leaves behind. Instead of dark mineral smoke, the plume can look pale, almost milky, because different compounds are crystallizing as the fluid mixes with seawater. The chimneys can look lighter too, with textures that feel more like layered pottery than jagged metal. These cooler systems can be just as alive as their hotter cousins, yet the cast of characters may shift. Chemistry decides who thrives. The microbes at the base can favor different reactions. and that shapes which animals can tap into the food supply that microbes create. White smokers are a reminder that the deep sea is not one uniform extreme. It is a spectrum of conditions, and life has learned to take advantage of subtle differences, even when the sun is far above and out of reach. Vent ecosystems run on chemosynthesis, not sunlight-powered photosynthesis. On land, food webs begin with light. Down here, they can begin with chemicals. Certain microbes use energy stored in compounds like hydrogen sulfide to build sugars and other organic matter, turning raw chemistry into living fuel. That makes these places feel like biology with a different set of rules, where a meal comes from reactions in water, not from leaves and chlorophyll. Once microbes start producing food, the rest of the community can follow. Grazers can scrape microbial films, filter feeders can capture drifting particles, and predators can hunt in the crowded darkness. It is an ecosystem built around invisible transactions, with energy passing from molecule to cell to animal. This matters beyond wonder. It shows that life can flourish without sunlight, and it expands our imagination about where biology might exist in other oceans, on other worlds. Giant tube worms have no mouth, yet their symbionts feed them. These animals can look like bright banners rising from the seafloor, but their most important feature is hidden inside. They do not eat in the usual way. No mouth, no stomach, no chewing. Instead, their bodies house bacteria that act like internal chefs, turning vent chemicals into nourishment. The worm provides the bacteria with a protected home and a steady supply of the right ingredients, delivered through specialized tissues and blood chemistry tuned for the job. In return, the bacteria produce food that keeps the worm growing, sometimes to startling sizes for the deep sea. It is a partnership that feels almost like a living agreement, signed in biochemistry. The result is an animal that can thrive where most creatures would starve, because its meals are manufactured within. When you picture it, it is less like hunting and more like carrying a miniature ecosystem in your own body. Certain vent shrimp navigate using heat sensors and chemical cues. In a place where light is absent, finding a vent is not like spotting a lighthouse. It is more like tracking a scent on shifting currents while staying close enough for food, yet far enough to avoid being cooked. Some vent shrimp manage this balancing act with sensors that seem almost futuristic. They can detect temperature gradients that change over inches, and they can follow chemical signatures that leak from the vent flow. That guidance helps them locate the right zone, where microbial growth is richest and conditions are survivable. They also live in a crowded world, where surfaces can be coated with bacteria, and where every crevice can matter. Their behavior becomes a kind of dance, moving with the currents, adjusting to heat, and responding to changes in vent output. It is navigation by physics and chemistry, and it turns an unseen landscape into something they can read, like a map written in warmth and molecules. Cold seeps leak methane and oil, supporting dense communities in darkness. Not every deep-sea oasis is powered by heat. Cold seeps can form where fluids seep out of the seafloor, at temperatures close to the surrounding water, yet the chemistry is rich enough to feed life. Methane and other hydrocarbons rise through sediments, and microbes begin to process them, building the base of a food web in a slow, steady way. Over time, this can support thick clusters of clams, mussels, and tube, like animals that gather where the seep is strongest. The scene can look like a bustling city block on an otherwise open plain. These seeps can persist for long periods, and they can also shift, migrate, or fade as underground pathways change. They matter for another reason too. They show how carbon can move from deep reservoirs into ocean systems, and how biology can intercept that movement, transforming it before it spreads. Brine pools form underwater lakes so salty many animals cannot enter. In certain places, the seafloor holds basins filled with brine that is far saltier than normal seawater. Because it is denser, it settles into depressions and forms a sharp boundary, like a shoreline you could trace in the dark. Animals that wander into it can be stunned or killed, not by teeth or claws, but by chemistry that overwhelms their bodies. That creates eerie edges where life gathers nearby, taking advantage of the unusual conditions without crossing the line. Microbes can thrive at the boundary, using the strong gradients in salt and chemicals, and larger creatures may hunt along the margins. These pools also preserve the idea that the ocean is not one single liquid environment. Even underwater, you can get layers that do not mix easily. It is like discovering a lake inside the sea, complete with its own rules, its own hazards, and its own strange opportunities for life. Some seafloor microbes live by consuming hydrogen made inside rocks. Deep below the seafloor, there are places where water and rock interact in ways that produce hydrogen gas. That hydrogen can become a fuel source, and certain microbes have evolved to harvest it. They do not need sunlight. They do not even need the dramatic spectacle of a hot vent plume. They can live in cracks and pores within the crust, in habitats that are more like a labyrinth than a landscape. Their world is defined by surfaces, minerals, and slow flows of water that carry reactants in and waste products out. This kind of life is easy to overlook because it is hidden and often sparse. Yet it may be widespread. It suggests that the ocean floor is not only home to animals we can film. It is also home to microscopic communities that run on basic chemistry, quietly transforming the crust and influencing what the ocean contains. Serpentinization can create energy-rich fluids without nearby volcanoes. Sometimes the most dramatic chemistry happens without an eruption. In serpentinization, seawater reacts with certain mantle rocks and changes them into new minerals. During that transformation, heat can be released, hydrogen can be produced, and the surrounding fluids can become chemically charged. This can set up conditions that support microbial life, even when there is no obvious volcanic heat source nearby. The process also changes the rock's structure, making it swell and crack, which can open new pathways for water to circulate and keep the reactions going. It is geology behaving like a slow engine, turning mineral change into usable energy. The idea is captivating because it feels like a blueprint for how environments can self-sustain in the deep, powered by rock and water alone. It also gives scientists a window into how Earth's interior interacts with the ocean, not only through lava, but through transformation that happens grain by grain. The Lost City vent field builds carbonate towers instead of sulfide chimneys. Lost City is famous because it looks like a different kind of vent world. Instead of dark, sulfide-rich chimneys, it builds pale towers made largely of carbonate minerals. The structures can be tall and intricate, and their shapes suggest long-lived flow through a complex plumbing system. The chemistry is unusual too, with fluids shaped strongly by reactions between seawater and mantle rocks, and with conditions that can support distinctive microbial communities. This is not a scene of constant volcanic blasting. It is a steadier kind of activity, where the architecture grows through ongoing mineral deposition. For scientists, it is a clue that vent-like systems can come in multiple styles, each with its own energy sources and biological possibilities. Lost City also captures the imagination because it hints at ancient Earth. It offers a living example of how chemistry, rock, and water can combine to create habitable niches that do not depend on sunlight and do not require a nearby eruption. Methane hydrates trap gas in ice, even in deep-sea sediments. Down in cold, high-pressure seafloor sediments, methane can become locked inside a crystal cage of water. It looks like ice, yet it can hold a fuel. bring it to warmer, lower pressure conditions, and it can fizz and release gas, which is why it sometimes earns the nickname burning ice. These deposits form where methane is produced or delivered, and where temperature and pressure line up just right. They matter because they store carbon in a concentrated form, and because they can influence slope stability when conditions change. Scientists study them with cores, seismic surveys, and careful lab tests, because disturbing them can alter the very thing you are trying to measure. It is a strange idea to hold in your mind. The seafloor can hide an icy lattice that is not only frozen water, but also a vault for gas. Massive submarine landslides can move more sediment than rivers deliver yearly. On land, landslides can feel dramatic. Underwater, they can be vast, and almost no one sees them happen. When a slope of sediment finally gives way, it can peel loose in a moving sheet, then break into a flowing mass that spreads across the deep. The volumes can be enormous, enough to rearrange whole sections of the seabed and bury habitats in a single event. Triggers can include earthquakes, rapid sediment buildup, or the weakening of layers that were stable until one moment. Afterward, the evidence can remain as headwall scars, jumbled blocks, and wide debris fields. These slides also matter because they can disturb seafloor infrastructure and, in some cases, contribute to tsunamis. What makes them so gripping is their scale. A quiet continental slope can hold a hidden instability and then rewrite the landscape with one decisive motion. Turbidity currents can race along the seafloor faster than a cyclist. Imagine a cloud of sand and mud, thicker than the water around it, suddenly spilling downslope and gathering speed. That is a turbidity current. It flows because suspended sediment makes the mixture denser, so gravity keeps pulling it along the bottom. As it races, it can scour channels, leap over small rises, and carry grains from shallow shelves into the deep ocean. It is not just fast. It is persistent, sometimes traveling for astonishing distances before it finally slows and drops its load. When the flow settles, it can leave layered deposits that look like pages in a book, each pulse forming a new sheet. These currents can also snap seafloor cables, which is one way humans have learned they exist, through sudden breaks far offshore. The deep sea can have floods, and they are made of sediment. Underwater canyons funnel sand and mud into the deep ocean. Along many continental margins, the seafloor is carved by canyons that look like river valleys, except they lead into darkness instead of into plains. They can begin near the shelf edge, then cut down the slope in winding paths, with branching side channels and steep walls. These canyons act like delivery routes, directing sediment from coastal regions toward deep basins. Storms, floods, and slope failures can feed them, sending material into the canyon head, then onward in pulses that move far from shore. Over time, these pathways can build deep sea fans, broad spreads of sediment that accumulate where the canyon flow finally loses energy. Canyons also influence biology because they can concentrate organic matter and create varied habitats along rugged terrain. They are reminders that the ocean floor is not only shaped by slow settling. It can be sculpted by focused transport, with channels that guide the sea's hidden cargo. Abyssal hills cover huge areas, formed as new crust cools and cracks. If you could fly low over much of the deep ocean, you would not see a smooth plain. You would see countless small ridges and swells rolling like a field of frozen waves. These are abyssal hills, and they form as young oceanic crust cools, contracts, and breaks along faults. The spacing and shape can reflect how the crust was made at the ridge, and how it stretched as it moved away. Over immense areas, these hills become the default texture of the seafloor, quietly controlling how sediments drape and how bottom currents weave through the terrain. They also create a patchwork of microhabitats, because slopes, crests, and valleys can differ in exposure and sediment cover. Abyssal hills are easy to overlook because they are not towering. Yet they are everywhere, and they make the deep ocean floor feel alive with structure, even in the farthest basins. Sediment can take thousands of years to build a single finger-width layer. Down in the deep, the seafloor can feel like a patient archive, and the pace of accumulation is part of the wonder. Tiny particles drift down from the water above, and each one settles as if it is arriving late to a very long story. A thin layer that looks ordinary in a core can represent stretches of time that outlast empires. The slow pace matters because it means many deep sediments are delicate records. A disturbance can erase what took ages to form. It also means changes stand out when they happen, like a sudden shift in grain size, a pulse of material, or a chemical signature that does not match the layers around it. Scientists treat cores with care for this reason. You are not just holding mud. You are holding time. The deep ocean writes slowly, and that slowness lets it preserve details that would be lost in faster, noisier environments. Some deep-sea mud is made mostly of microscopic shells. In many parts of the ocean, the seafloor is carpeted with the remains of plankton so small you could fit thousands on your fingertip. When these organisms die, their tiny shells drift downward, and over long spans they accumulate into a soft, pale mud. The shells can be made of calcium carbonate or silica, depending on the plankton, and each type tells a different story about surface waters where the organisms once lived. In the lab, scientists can sort and identify these microfossils, and those identifications can reveal past temperatures, nutrient conditions, and even patterns of ocean circulation. It is a powerful idea. A deep seabed that looks plain can be built from countless minute skeletons, each one a clue from the upper ocean. The deep floor becomes a library of vanished surface life, stacked in layers that can be read with microscopes and patience. Red clay accumulates so slowly that time is measured in millions of years. Far from land and far from abundant biological debris, some parts of the deep ocean receive only a whisper of material. Over vast expanses, what settles can be fine dust, tiny mineral particles, and trace components that tint the sediment a rusty red. Because the supply is so sparse, the buildup is extraordinarily slow. A small amount of thickness can represent an almost unimaginable span of time. This is why red clay can feel like the deep ocean's most minimal diary. It records the background rhythm of the planet, not the loud events. It can also preserve unusual materials, because the slow pace means there is less dilution from other sediment sources. Scientists who work with it must think in very long chapters. When you look at red clay, you are looking at a place where the sea floor has waited and waited and waited, collecting the faintest rain of particles, while the world above changes again and again. The carbonate compensation depth marks where shells dissolve faster than they fall. In the ocean, chemistry changes with depth, and that chemistry decides what survives the descent. At a certain level, calcium carbonate becomes less stable, and shells made of it begin to dissolve more readily. Below that boundary, fewer carbonate shells accumulate on the seafloor, even if many were produced at the surface. This depth is not a fixed line carved into the planet. It can shift with temperature, carbon dioxide levels, and circulation, which makes it a sensitive marker of ocean conditions. It also shapes what kinds of sediments form in different basins, and it affects how the ocean stores carbon over long spans of time. The idea is both simple and profound. A drifting shell might begin as a sturdy structure in sunlight, then quietly vanish on its way down, erased by water chemistry before it ever reaches the bottom. The seafloor record depends on where that invisible boundary sits. Silica ooze comes from glassy plankton skeletons drifting down from above. Some plankton build their bodies from silica, forming intricate skeletons that can look like tiny stained glass when seen under a microscope. When these organisms die, their silica structures sink, and in the right regions they accumulate into a soft sediment called silica ooze. This tends to happen where silica is plentiful in surface waters, and where conditions allow enough of it to survive the journey downward. Over time, that ooze can compact and transform, and it becomes part of the geological record in a way that feels almost poetic. The deep ocean can be seeded by the architecture of minute living things. Silica ooze also helps scientists trace past productivity and ocean circulation, because its distribution depends on where those plankton flourished. It is another reminder that the seafloor is not only shaped by rock and gravity. It is shaped by the slow snowfall of biological structures built in the light, then stored in the dark. Manganese nodules grow so slowly that they challenge our idea of time. These lumps sit on the abyssal plains like scattered potatoes, and their pace of growth is almost unbelievable. Layer by layer, metals precipitate from seawater and pore water, coating a small starter such as a shark tooth fragment or a bit of shell. Over spans that make human history feel brief, a nodule can creep outward by tiny amounts, building a hard rind around its core. Because they form in open, deep ocean settings, they can capture a chemical snapshot of the water that bathed them as they grew. That makes them both a curiosity and a record. They also create habitat, with hard surfaces in places otherwise dominated by soft mud, giving small animals somewhere to cling. When you hold the idea of a nodule in your mind, it feels like the seafloor, practicing patience, turning dissolved traces into stone, one quiet layer at a time. Ferromanganese crusts coat seamounts, concentrating rare metals over ages. On some underwater mountains, bare rock is slowly varnished by a dark coating, and the coating keeps thickening over very long spans of time. These crusts form where currents sweep the seamount flanks, keeping sediment from burying the surface and allowing minerals to accumulate directly on exposed rock. As the crust grows, it can gather elements that are scarce elsewhere, including metals used in modern technology. That makes these coatings scientifically intriguing and economically tempting, which is why they sit at the center of difficult debates about exploration and disturbance. The crust itself becomes a kind of timeline, with chemical layers that reflect changes in seawater over ages. It also changes the seamount habitat, turning rough volcanic rock into a different texture that can influence which organisms settle there. A seamount can feel like a mountain range with a slow-forming skin, written by chemistry and shaped by currents. The abyssal seafloor holds more undiscovered species than many rainforests. Down in the deep, new creatures are often found not because they are rare, but because we have barely looked. The abyss covers enormous areas, and much of it is hard to reach. So even a single expedition can bring back animals that do not match anything described before. Some are tiny and delicate, living between sediment grains. Others are strange in shape, with soft bodies built for low-energy living. There are also communities that appear only in certain patches, tied to currents, food supply, or the presence of hard surfaces. Every sample can expand the tree of life, and that is thrilling, because it means the largest habitat on Earth is still full of unknown stories. This also raises a practical question. If we do not know what lives in a place, how can we judge what might be lost there? The abyss keeps its secrets well, and science is still learning how to ask. Xenophyophores are giant single cells that build homes from sediment grains. It sounds like a creature from fiction, yet it is a single cell, that can grow to the size of a hand. Instead of having bones or a shell like an animal, it gathers sediment particles and uses them to construct a complex branching structure on the seafloor. Inside, it organizes its living material in a way that lets it spread across a wide area, interacting with the mud and the water just above it. These structures can become mini habitats, offering shelter and surfaces for small animals that would otherwise have few places to hide. Xenophyophores also hint at how flexible life can be. A single cell can behave like a tiny ecosystem engineer, shaping its surroundings and changing who can live nearby. They remind us that size is not reserved for multicellular life, and that the deep ocean can turn even the simplest forms into architects. Some deep-sea fish make their own light using symbiotic bacteria. In the dark, light becomes a tool, and some fish outsource that tool to living partners. They host bacteria in special organs, and those bacteria produce a steady glow that the fish can control by shading it, opening it, or aiming it. This can help with hunting, because a small light can draw curious prey close. It can help with hiding too, by matching the faint downwelling glow from above in shallower depths, which reduces the fish's silhouette when seen from below. In some species, light is also a signal, a way to communicate in a world where color and pattern vanish. The partnership is precise. The fish must provide nutrients and a safe place to live, and the bacteria must deliver reliable light. It is a biological agreement that turns microbes into equipment. When you imagine it, it feels like the deep sea inventing its own language of lanterns, carried on fins. Bioluminescent flashes can confuse predators and attract mates in total darkness. A sudden burst of light in the deep can be a warning, a trick, or an invitation. Some animals release clouds of glowing material that hang in the water like a decoy, giving the animal a moment to escape while the predator strikes at the wrong target. Others flash in patterns that appear to be specific to their species, which helps potential mates find each other in an environment where distance feels endless. There are also creatures that use light as bait, wiggling a luminous lure to draw prey within reach. The deep sea is full of these strategies because light is rare, and rare things become powerful. What makes this so captivating is the speed. The flash is brief, yet it can decide survival. In a place where sound and scent travel, a pulse of light can still cut through, like a secret signal. Darkness is not empty down there. It is filled with messages. Whale falls create temporary oases, feeding seafloor life for decades. When a whale dies and sinks, the deep seafloor receives a sudden gift of concentrated food. Scavengers arrive first, stripping soft tissue and leaving a skeleton that can still feed life for years. As the bones are broken down, they can release compounds that support bacteria, and those bacteria can form the base of a new community. Over time, the site can host changing groups of animals, like a neighborhood that evolves from one set of residents to another. This matters because the deep ocean often runs on scarce supply, and a large carcass is an event, not a routine. It can connect ecosystems too, because animals that specialize in these falls may travel long distances to find them. Each whale fall is both a meal and a habitat, and it turns death into a long unfolding story on the seabed. For scientists, it is a natural experiment in how life responds to abundance in the deep. Bone-eating worms colonize whale skeletons, using unusual acid chemistry. These worms look delicate, but their lifestyle is bold. They settle on bone and then extend root-like tissues into it, accessing nutrients locked inside the skeleton. To do this, they rely on chemistry that helps dissolve and penetrate hard material, and they host microbes that assist with processing what they extract. They do not have jaws that chew bone into pieces. Instead, They use a method that feels more like mining, slowly tapping a resource that few other animals can use. This makes them specialists in an ecosystem that appears only when a large carcass reaches the deep. Their presence also changes the pace at which the skeleton is broken down, which influences how long the whale fall remains a habitat. Bone-eating worms remind us that nature does not waste much. Even the hardest parts of a giant animal can become food, if evolution finds the right tools. Many deep-sea animals grow slowly, because food arrives as a thin rain. On the abyssal floor, a meal often begins far above, as small bits of organic matter drift down from surface waters. By the time it reaches the bottom, it can be sparse and scattered, which means many animals must live with long gaps between feasts. That scarcity shapes their entire way of being. Metabolisms can be low. Movements can be measured. Lifespans can stretch longer than you might expect, because growing fast is risky when calories are unpredictable. Some animals also become opportunists, ready to rush toward a fresh food fall when it appears, then settle back into patience afterward. The result is a deep community tuned to endurance rather than speed. This slow growth is not a sign of weakness. It is a strategy for a world where energy is precious and every bite matters. When you picture the deep sea, it helps to imagine time moving differently, paced by the arrival of food. Marine snow is mostly leftovers, yet it fuels whole ecosystems below. This steady fall is made of tiny fragments, bits of dead plankton, shed mucus, fecal pellets, and other organic crumbs that clump together as they sink. It drifts downward in soft flurries, and it is one of the main ways energy moves from sunlit waters to the dark seafloor. Along the way, it is grazed, broken apart, and repackaged by microbes and small animals, which changes what finally reaches the bottom. When it does arrive, it feeds worms, crustaceans, sea cucumbers, and countless microorganisms that live within the sediment. In some seasons, the snowfall thickens after surface blooms, and the bottom community can respond like a town receiving deliveries after a long, lean period. The idea is humbling. The deep ocean is supported by what the upper ocean discards. Leftovers become lifelines, and the slow fall ties the surface world to the planet's hidden foundation. Benthic storms can sweep the abyss, resuspending sediment like a blizzard. Down in the deep, the water can suddenly pick up speed, and the bottom responds. Fine sediment lifts off the seabed and hangs in the water, turning clear darkness into a drifting haze. For animals that filter feed or breathe through delicate surfaces, that change can be like weather moving through a town. Some creatures hunker down. Others take advantage, because stirred-up particles can carry food that was buried. Instruments on the sea floor have recorded these events arriving and fading, showing that even the abyss has bursts of motion that are not obvious from the surface. Afterward, the settling can smooth small features and shift the pattern of where organic matter lands. It is a reminder that the deep ocean is not always still. Sometimes it has storms with no lightning, no wind, and no clouds, only moving water and a seabed briefly set free. Contour currents sculpt deep drifts, flowing along the edges of continents. Along the continental margins, deep currents can travel like steady rivers, sliding parallel to the slope instead of rushing straight down it. Over time, these flows can pick up fine sediment in one place and lay it down in another, building long mounds and ridges called contoured drifts. The shapes can be broad and graceful, and they can stretch for great distances, recording how currents have behaved over very long spans. Scientists read these deposits to learn about past ocean circulation, because changes in the drift can hint at shifts in water mass strength and direction. These currents also influence where the seafloor is firm or soft, which matters for the animals living there. It is a different kind of seafloor sculpting. No landslide drama and no volcanic construction. Only patient motion along the edges of continents, building landforms by rearranging dust like a slow, invisible hand. Some C4 bacteria fix nitrogen, influencing ocean chemistry far above. In the dark on the ocean floor, some microbes perform a job that helps set the rules for life in the sea. They can convert nitrogen gas into forms that other organisms can use, adding usable nitrogen to environments where it can be scarce. That matters because nitrogen is a key ingredient in proteins and DNA, and it can limit how much life can grow in the waters above. In some settings, these microbes live within sediments, where oxygen and nutrients change over small distances, creating pockets where certain reactions become possible. Their work does not look dramatic, yet it can influence the chemistry of pore water, the cycling of nutrients, and the overall balance of the ocean's productivity. It is an elegant idea. Tiny organisms hidden in mud can help regulate the ingredients that shape ecosystems on a far larger scale. Hadal amphipods survive the deepest trenches, with membranes tuned for pressure. In the deepest trenches, small crustaceans called amphipods can thrive where almost nothing seems built to function. Their bodies are adapted for a world that presses in from every direction, and a big part of that adaptation lives at the cellular level. Membranes have to stay flexible, because if they become too rigid, basic processes can fail. These amphipods also have to solve the problem of finding food in a place where meals can be rare and scattered. Some gather around fallen organic material. Others patrol the bottom like persistent scavengers. Researchers have brought them up from great depths and studied how their tissues cope, revealing survival strategies that are both chemical and structural. What makes them fascinating is their size compared with their environment. A small animal only inches long can live in a realm deeper than the tallest mountains are high, as if the trench itself is their normal neighborhood. Trench snailfish are among the deepest known fish, adapted to crushing depths. A fish living in a trench must deal with pressure that would overwhelm most vertebrates, yet some snailfish manage it with a suite of deep adaptations. Their bodies tend to be soft and flexible, which helps them avoid rigid structures that pressure could compromise. Their proteins and cellular chemistry are adjusted so that vital reactions can still run under extreme conditions. Even their lifestyle fits the trench. They often feed on small crustaceans, taking advantage of prey that can be abundant in certain trench zones. Seeing them on deep cameras can feel almost surreal, because a familiar animal shape is moving calmly in a place that seems impossible for fish. For scientists, these fish are a test of biological limits, showing how far vertebrate life can push into the deep. They also raise new questions, because each deeper observation forces a rethink of where the boundary of survivable depth might really lie. Not all trenches are the same, each has its own geology and life. It is tempting to imagine trenches as one repeated feature, but each one is its own world. Some are fed by heavy sediment flows from nearby land, while others are relatively starved, leaving different kinds of seabed and different chemistry. The shape can vary too, from steep and narrow to broader with terraces and basins, and those shapes influence how material moves and where it settles. The water above can also differ, with changes in temperature, oxygen, and food supply that shape what can live on the bottom. Even the way a plate dives can matter, because it affects faulting, fluid release, and how the trench evolves over time. This means trench biology is not a single story. It is many local stories, each tuned to its setting. Exploring a new trench is not like revisiting an old one. It is like stepping into a new region with its own rules, its own residents, and its own surprises. The Mariana Trench includes Challenger Deep, Earth's deepest known point. Challenger Deep sits within the Mariana Trench, and it represents the lowest known spot in the global ocean. Getting there is hard because the descent takes hours, communication is limited, and the environment is unforgiving. Yet it has been visited, measured, and studied with a mix of crewed dives, landers, and remote vehicles, each adding pieces to the picture. The seafloor at that depth is not bare rock. It is often fine sediment, shaped by the trench's geometry and by the slow arrival of material from above. Life exists there too, not as a lush reef, but as hardy organisms that have made an extreme habitat workable. Challenger Deep matters because it is a benchmark. It is a natural limit case for exploration, engineering, and biology. Each mission there is a reminder that our planet still has places that require the best of human curiosity and the most careful design. Ocean trenches can trap plastics, carrying surface waste into the abyss. Trenches act like deep collecting basins, and modern debris can end up there. Floating plastics can break into smaller pieces, become heavier as organisms grow on them, or get swept into pathways that move material downward. Once in the deep, the trench shape helps retain what arrives, because steep walls and confined basins can limit how easily particles are stirred back out. This is unsettling, because it means human influence can reach even the most remote parts of the ocean floor. It also complicates science, since deep ecosystems that evolved over long spans now encounter materials that did not exist in nature. Researchers study how this debris moves, how it fragments, and how it interacts with sediments and organisms. Trenches are often described as Earth's deepest places. The fact that they can also become repositories for modern waste is a sharp reminder that distance does not guarantee protection, and that the ocean is connected from the surface to the depths. Microplastics have been found in deep sediments, mixing into the seabed. When plastics break into tiny fragments, they can behave like grains of sand, drifting, settling, and becoming part of the sediment itself. In the deep sea, that means microplastics can end up mixed into the seabed, where worms, crustaceans, and microbes interact with particles every day. This raises difficult questions. Do these fragments change how sediments hold water and oxygen? Do they carry chemicals or provide surfaces for microbes in ways that alter normal processes? Can they move through food webs when sediment feeders ingest them? Scientists investigate by sampling cores, separating particles, and comparing sites, because the deep ocean is vast and patterns vary. The finding is sobering, but it is also scientifically revealing. It shows how efficiently the ocean transports materials and how the deep seabed can become a long-term archive of human activity. What settles there can persist, quietly reshaping the background conditions of life on the bottom. Deep sea corals grow on seamounts, and some live for centuries. On seamount slopes, corals can anchor to hard rock and build branching structures that look like underwater trees, even though no sunlight reaches them. They feed by capturing particles and small prey carried by currents, so the best coral gardens often form where flow delivers a steady supply. Because growth can be slow, some colonies can persist for very long spans, becoming living records of the conditions around them. Their skeletons can store chemical clues about the water they grew in, which gives scientists another way to study ocean history. These corals also create habitat. Their branches offer shelter and feeding grounds for fish and invertebrates that might otherwise have few places to gather on a rocky slope. When you imagine a coral colony holding on for centuries, you start to feel the deep sea's timescale. A storm on the surface is a moment. A coral garden on a seamount can be a long-lived community, built patiently in darkness by steady currents and persistent life. Sponge fields can be vast, turning seafloor currents into living filters. In some deep regions, the bottom is not empty mud. It is a patchwork of sponges, standing upright like a slow-moving forest. Each sponge pulls water through its body, trapping bacteria and organic particles, and releasing cleaner water back out. When thousands of them work at once, a current passing over the field is changed by biology. Food is intercepted. Nutrients are transformed. Tiny animals find shelter in the sponge structures, and predators learn to patrol the edges. Some sponge grounds form in places where currents are steady, and the seafloor is firm enough to anchor them, which means they can become reliable hotspots in an otherwise sparse deep sea. The most striking part is scale. A sponge can seem simple when you see one. A field of them becomes an ecosystem engineer, reshaping how water and food move across the seabed. Some sponges make chemicals now studied for medicine and disease research. A sponge cannot run away, so chemistry becomes part of its defense. Many produce compounds that discourage microbes, deter predators, or prevent other organisms from overgrowing them. Those same molecules can be interesting to humans because they interact with cells in precise ways. Researchers have investigated sponge-derived chemicals for roles that include antiviral, antibacterial, and anti-cancer activity. And the hunt continues because the ocean's chemical diversity is immense. The deep sea adds another twist. Conditions are stable, competition can be fierce on hard surfaces, and slow-growing organisms may invest heavily in chemical protection. Collecting samples requires careful work because you want to study the chemistry without destroying the habitat that makes it possible. Is this one of the deep ocean's most surprising gifts? A creature that looks like a simple filter can hold molecular tools that inspire new ideas in medicine, or because survival demanded creativity. Chemosynthetic clams host bacteria inside their tissues, like living power plants. Some deep-sea clams do not rely on drifting scraps from above. They bring their own food makers. Inside their bodies, they house bacteria that can turn chemicals from seafloor fluids into usable energy, then into nourishment. The clam supplies a protected home and access to the right ingredients, often by extending into sediment where those chemicals seep upward. In return, the bacteria provide a steady food source, which allows the clam to thrive where normal feeding would not be enough. You can find dense beds of these clams in places where the chemistry is right, making the seafloor feel busy and alive in the darkness. What makes this so captivating is the teamwork. It is not a single animal succeeding alone. It is an alliance that turns an invisible chemical leak into a long-term living community, anchored in mud and sustained by microscopic partners. Giant isopods roam the deep, related to familiar woodlice on land. At first glance, a giant isopod looks like a creature from a forgotten age. It has a plaited shell, many legs, and an almost armored calm as it walks across the seabed. Yet it is part of a group that includes small woodlice you might find under a log. The deep-sea version can grow far larger, and it lives a life tuned to long waits and sudden opportunity. Food can be unpredictable, so these animals are built to endure lean stretches, then make the most of a rare feast when it appears. They can curl into a protective ball, and they use their strong limbs to cling, climb, and forage across uneven bottom terrain. Seeing one on deep camera footage is always a shock, because it makes the deep ocean feel connected to your backyard, while also reminding you that evolution can stretch a familiar body plan into something monumental. Many seafloor creatures use smell more than sight, because light never reaches. In the deep, vision often becomes secondary, and chemistry becomes the main language. A small trace of odor can signal food, danger, or a potential mate, and the water carries those clues along currents like invisible ribbons. Many bottom dwellers have sensitive antennae, tentacles, or other structures designed to sample the water and read it. A scavenger may follow a scent trail across the seabed, the way a dog follows a path on land, except the trail can lift, twist, and thin as the current shifts. This makes the deep sea feel alive, with information that humans do not naturally perceive. It also shapes behavior. Animals may pause, test the water, then change direction with sudden certainty. When you imagine the deep seafloor, it helps to imagine a world where the most important signals are not seen, but tasted in the water, and where a successful life depends on interpreting faint chemical whispers correctly. Hydrophones reveal that the deep sea is noisy with earthquakes and ice. The deep ocean is dark, but it is not silent. Hydrophones, underwater microphones, pick up a constant soundtrack. Some sounds come from the earth itself, with distant earthquakes sending low vibrations through the crust and water. Other sounds can arrive from far away, including the cracking and grinding of ice in polar regions, which can travel astonishing distances underwater. Storms at the surface also contribute, and so does the chorus of marine life in certain places. Researchers use these recordings to monitor seismic activity, study ocean processes, and track how sound moves through different water layers. Listening becomes a kind of remote exploration because sound can reach where cameras cannot. The idea is beautifully strange. You can sit on a ship or even analyze data on land and still hear the planet flexing, fracturing, and shifting beneath the waves. The seafloor announces its activity, not with light, but with vibration. The seafloor is laced with cables that carry most global internet traffic. Beneath the oceans, long cables lie on the bottom and connect continents with streams of data. They cross plains, skirt around rugged features, and descend into deep basins where the terrain is stable. Engineers choose routes carefully, avoiding steep slopes, active hazards, and places where fishing more anchors could cause damage in shallower water. These cables are protected and monitored, yet the environment still matters. Earthquakes, landslides, and strong currents can threaten segments, and repairs can require specialized ships and precise work in open ocean. It is a striking modern layer to add to the ancient seafloor story. On the same terrain where new crust forms and sediments gather over ages, messages, calls, and videos travel as pulses of light through glass fibers. The ocean floor is not only geology and biology. It is also infrastructure, quietly supporting everyday life above the waves. Shipwrecks become reefs on the bottom, creating new habitats over time. When a ship settles onto the seafloor, it becomes more than a relic. Its hard surfaces offer footholds in places where the bottom might otherwise be soft and featureless. Over time, organisms can colonize the metal and wood, building layers of life that attract more life. Fish may use the structure for shelter. Invertebrates can attach and spread. Microbes begin the slow work of altering and corroding materials, which changes the chemistry around the wreck. Each wreck becomes a small experiment in how habitats form when new structure appears. The story differs by depth, currents, and water chemistry, so one site might become a thriving community, while another remains sparse and austere. There is also a human element. Wrecks can preserve history, and they can raise questions about protection and disturbance. On the seafloor, even our accidents can turn into ecosystems, give them enough time. Deep-sea mining targets nodules and crusts, raising difficult conservation questions. Some parts of the deep seabed hold mineral deposits that formed over immense spans, and modern industry has begun to eye them as potential resources. The challenge is that extracting them would disturb habitats that are slow to form and still poorly understood. Removing nodules, for example, also removes hard surfaces that certain animals rely on, while stirring sediment can create plumes that spread beyond the immediate area. Because deep ecosystems often develop slowly, damage could persist for long periods, Scientists, policymakers, and communities debate how to weigh potential benefits against risks and how to study impacts before decisions become irreversible. There is no simple narrative here, only a real-world tension between demand and stewardship. The ocean floor feels remote, yet choices made about it can echo widely. It is a place where curiosity, technology, and responsibility meet, and where the unknown should encourage caution rather than haste. Some abyssal species may take decades to recover from disturbance. In the deep, many animals grow slowly, reproduce slowly, and depend on stable conditions. When the seabed is disturbed, whether by trawling, heavy equipment, or sediment plumes, the recovery can be nothing like a quick rebound on land. Burrows collapse. Feeding surfaces are buried. The pattern of oxygen and nutrients in the sediment can shift, which changes what microbes and small animals can do there. For species that live for a long time and spread gradually, recolonizing an altered patch can take years, and in some cases, far longer. Even if individuals return, the original community structure may not, because the disturbance can change the habitat itself. This is why deep-sea impact studies focus on timescales that feel unfamiliar. It is not about weeks. It is about decades and beyond. The abyss teaches a simple lesson. When life is slow, healing is slow too. Seafloor mud preserves ash layers from ancient eruptions, like timestamps. When a volcano erupts, the drama can end quickly in the air, but it can continue quietly in the deep. Fine ash can drift over the ocean, settle through the water column, and land on the seafloor as a thin, distinctive layer. Long after the sky clears, that ash remains, sealed within mud, like a page marker in a book. Later, sediments build on top, protecting it from waves and weather that would erase the same evidence on land. In a core sample, an ash layer can stand out by color, texture, and chemistry, and it can often be matched to a known eruption region. That gives scientists a precise checkpoint in time, which helps them compare records from different places. It is also a reminder that the ocean floor does not only record slow change. It can capture sudden events, then hold them patiently for ages. Tiny fossils in sediments help date the ocean floor with surprising precision. In many seafloor sediments, the most useful clocks are almost invisible. Microscopic plankton once floated near the surface, lived brief lives, then sank when they died. Their shells became part of the seafloor, and over time, they built layers filled with recognizable species. The key is that certain microfossils appear, evolve, and disappear in known sequences. When scientists identify them in a core, they can estimate the age of each layer and the pace at which sediment accumulated. This turns mud into a timeline, and the timeline can be surprisingly detailed. It can reveal when currents shifted, when productivity changed, and when conditions in the upper ocean favored different life. The thrill is that you do not need a giant skeleton to learn history. A dusting of tiny shells can anchor an entire story of ocean change, one layer at a time, across spans far beyond human memory. Ocean crust is usually younger than continents because it is recycled. Continents can linger for billions of years, but ocean crust rarely gets that kind of longevity. It forms, cools, and then begins a slow journey across the basin until it meets a subduction zone where it bends and dives back into the mantle. That return trip acts like a built-in expiration date. The ocean floor is constantly renewed, while continents behave more like long-lived archives. This difference shapes the entire surface of Earth. It affects where mountain ranges rise, where volcanic arcs form, and why seafloor ages create broad patterns across the oceans. It also means the ocean floor holds a younger, clearer record of plate motion, because older chapters are often erased by recycling. When you picture Earth's crust as two different lifespans, the planet makes more sense. Continents are durable libraries. Ocean crust is a circulating system, always being written, carried, and rewritten. The oldest ocean floor is still ancient, but far younger than most land. Even the old seafloor has a limit, and that limit says something profound about how Earth works. Because ocean crust is routinely consumed at subduction zones, the oldest remaining patches are not as old as the oldest continental rocks. They can still be ancient in human terms, yet they represent only a fraction of Earth's full history. This shapes what we can know. If you want to read the earliest chapters of the planet, you often look to continents. If you want to read the recent choreography of plates and oceans, you look to the seafloor. The contrast is like comparing a long-lived tree with a field that is replanted again and again. The field can show you what has happened lately with clarity, but it cannot preserve the oldest rings. The ocean floor is a remarkable archive, and it is also a reminder that the planet edits itself, removing older pages as it builds new ones. Drilling programs have retrieved cores that record millions of years of change. Some of our best deep ocean discoveries come not from cameras, but from cylinders of mud and rock lifted from far below. Scientific drilling has allowed researchers to sample sediments that built up over immense spans and to reach deeper into the crust beneath them. Each core is a physical history you can hold, with layers that track shifts in temperature, ice volume, ocean chemistry, and biological productivity. The power is in continuity. A long core can show slow trends, sudden disruptions, and cycles that repeat, all stacked in order. It can also reveal how fast certain changes happened, which helps scientists test ideas about climate and circulation. Getting a core is not simple. It requires ships, careful planning, and precise handling so layers are not disturbed. Yet the reward is extraordinary. The seafloor becomes a storyteller, offering a record that often cannot be found on land, because land erodes while the deep ocean quietly accumulates. Methane seeps can build carbonate rocks that look nothing like beach limestone. At methane seeps, chemistry can turn the seafloor into a construction site. Microbes consume methane in reactions that change the surrounding water chemistry, and those changes can cause carbonate minerals to precipitate within sediments or on the surface. Over time, this can create hard crusts, chimneys, and irregular slabs that seem out of place in soft mud. The rocks are carbonates, yet they are not the familiar products of shallow reefs or warm beaches. They are born from seep chemistry in darkness, often in shapes that look jagged, knotted, or honeycombed. These structures can become habitat, offering firm surfaces where animals can attach and where communities can gather around the seep's resources. For geologists, seep carbonates are clues to fluid flow and past seep activity. For everyone else, they are a surprising reminder that rocks can form quickly in the deep, not only through volcanoes, but through microbial chemistry that turns invisible gas into stone. Some deep sediments host microbes that divide only once in centuries. In the deep biosphere, life can move at a pace that feels almost unreal. Some microbial communities exist in sediments where energy is scarce and conditions change very slowly. Instead of rapid growth, these microbes may spend long spans maintaining themselves, repairing damage, and waiting for tiny pulses of usable energy. In such settings, cell division can be extraordinarily rare, and a single doubling can take centuries. That is not a poetic exaggeration. It is a reflection of strict energy budgets in deep sediments. This kind of life challenges how we define active. These microbes are not frozen. They are metabolizing, responding, and persisting, just at a tempo closer to geology than to everyday biology. It also changes how scientists search for life elsewhere, because slow does not mean absent. The seafloor teaches that biology can survive in the margins, living on almost nothing, and still remain alive in a meaningful way. The deep biosphere may contain a large share of Earth's microbial life. Beneath the seafloor, microbes live in sediments and within the oceanic crust itself, occupying pores, fractures, and thin films of water. This hidden realm is enormous in volume, and it extends across much of the planet's ocean basins. That means the number of microbial cells down there could represent a significant portion of Earth's total, even if the communities are sparse in any single handful of sediment. What makes this so compelling is the scale of the unseen. The surface ocean may look like the obvious place for life, yet the deep subsurface can host a vast, quiet biosphere that most people never consider. These microbes influence chemical cycles by transforming carbon, sulfur, and other elements, and they interact with rocks in ways that slowly alter the crust. Studying them is difficult, because samples must be collected without contamination and interpreted carefully. Still, every discovery expands the idea of what habitat means, and it hints that Earth's living inventory is deeper than our maps. Seafloor heat flow varies, revealing where crust is young or old. The ocean floor leaks heat from Earth's interior, but it does not leak it evenly. Newly formed crust near ridges is hotter, so it releases more heat. As crust ages, it cools, thickens, and sends less heat upward. By measuring heat flow, scientists can infer the relative youth or maturity of different seafloor regions, even when the rocks themselves are buried under sediment. These measurements also connect to circulation within the crust. In some places, seawater moves through cracks, picks up heat, and transports it, which can change the heat flow pattern and reveal hidden pathways. Heat flow maps become a kind of thermal fingerprint for the seafloor. They help test models of plate cooling, guide exploration of hydrothermal systems, and refine our understanding of how the ocean crust exchanges energy with the ocean above. It is a quiet signal with a big meaning. The seafloor is not only shaped by motion and chemistry, it is also shaped by heat, escaping steadily from below. Rifted ridges can expose mantle rocks directly on the seafloor. In some ridge settings, stretching and faulting can peel the crust apart in a way that brings unusually deep rocks to the surface. Instead of seeing only basalt formed from erupted lava, scientists can find mantle-derived rocks exposed on the seafloor, revealing material that usually stays hidden far below. This exposure offers a rare chance to study the ingredients of Earth's interior without drilling miles down on land. It also changes the chemistry of seawater-rock interaction, because mantle rocks can react strongly with water, producing distinctive fluids and new minerals. The terrain in these areas can look rugged and complex, with large faults, domes, and scarps that tell a story of tearing and uplift. For researchers, it is like finding the backstage of a familiar play. You can see how the crust is assembled and how the mantle participates, not only as a source of melt, but as a physical presence of the ocean floor. It is a glimpse into the planet's deep anatomy, brought up by the slow power of plate motion. Oceanic core complexes form when faults peel crust apart like a lid. In some parts of the mid-ocean ridge system, the seafloor is not built in neat layers of lava on top of deeper rocks. Instead, huge faults can slip for long periods, lifting deep crustal material up and rolling it outward like a slow opening door. The surface that emerges can look domed and sculpted, sometimes marked by long grooves that hint at the direction of motion. This is a rare window into the inside of oceanic crust, exposed without drilling, and it helps scientists test how plates stretch when magma supply is limited. These areas can also change local habitats, because different rocks weather and fracture in different ways. creating fresh surfaces for chemistry and life. It is tectonics you can almost picture with your hands. The planet stretches, a fault takes over, and the deep is turned outward for the ocean to touch. Submarine volcanoes can erupt quietly or explosively when gases escape. Underwater eruptions are not one single style of event. In deep water, pressure can keep gases dissolved, which often leads to calmer lava outpourings that build new rock without dramatic blasts. Move the eruption into shallower water, and the rules change. Gas can expand more easily, and hot magma meeting water can flash it into steam, shattering lava into fragments. That can produce ash, pumice, and clouds of debris that spread through the water column. Some eruptions build cones. Others lay down broad flows that smooth the seafloor, then crack as they cool. What makes this fascinating is that the ocean does not simply cover volcanoes. It actively shapes how they behave, how their materials spread, and how quickly new habitats appear. A submarine eruption can be a quiet construction project, or it can be an underwater demolition, depending on depth and chemistry. Lava flows can create new seafloor overnight, then cool for centuries. A patch of ocean floor can be transformed in a single day, with molten rocks spilling out, hardening, and becoming new ground. For a moment, the seafloor is a construction site, with fresh lava forming ridges, cracks, and bulbous shapes as it meets cold seawater. Then, the pace changes completely. Once the surface hardens, the new crust begins a long, cooling journey. Heat drains away slowly, the rock contracts, fractures open, and seawater can circulate through those cracks, carrying chemicals that alter the basalt over time. The same flow that formed quickly becomes a long-term experiment in cooling, cracking, and gradual change. That contrast is the wonder. Earth can create land at breathtaking speed, then spend an age adjusting it. The seafloor keeps both tempos at once, the sudden birth and the long settling. Hydrothermal circulation can alter crust chemistry, changing how rocks store water. Seawater does not only sit on top of the ocean crust. In many places it sinks into fractures, warms up, reacts with rock, and returns changed. During that journey, the crust itself changes too. Minerals can transform into new forms that include water within their structure, so the rock becomes hydrated, not just wet. This chemical remodeling can affect density, strength, and even how seismic waves travel through the crust. It can also move elements around, concentrating some and stripping others, which means the crust's composition is not fixed at birth. It matures, like wood seasoning over time. The process is hidden, yet it is widespread, and it helps explain why oceanic crust is such an active participant in Earth's water cycle. The ocean and the crust trade chemistry through countless cracks, turning solid rock into a moving, evolving system that can lock water away for very long spans. Water carried into subduction zones helps trigger melting that feeds volcano arcs. As oceanic plates sink, they do not go down dry. Hydrated minerals and water-rich sediments are carried with them, and increasing heat and pressure can force that water back out. Those released fluids rise into the mantle above the subducting slab, and they lower the melting point of surrounding rock. That is how a descending plate can help create magma far from the ridge where crust was born. The magma rises, collects, and can feed chains of volcanoes that curve along trenches, forming island arcs or volcanic mountain belts near continents. It is a circular story. Water helps build crust at ridges through melting, then water helps generate new melts again when that crust is recycled. This is not a small detail. It links the deep ocean floor to the volcanoes people live beside, showing how a molecule carried downward can return as fire, rock, and new land. Some seafloor sediments store carbon, influencing Earth's long-term climate balance. The deep seafloor is one of the planet's great storage rooms, and carbon is one of the main things it keeps. Organic matter can be buried in sediments before it is fully broken down, and carbonate shells can accumulate where ocean chemistry allows them to survive. Once buried, that carbon can stay out of the atmosphere for very long spans, especially when sediments are thick and undisturbed. Over time, some of this material can be carried into subduction zones, while some remains locked in place, compacting into rock and becoming part of the geologic record. This slow storage and release influences how much carbon dioxide is available to warm the planet, but it does so on timescales that feel almost beyond intuition. The seafloor is not just a stage for life. It is part of Earth's climate machinery, quietly balancing inputs and outputs through burial, chemistry, and deep time. Methane released from sediments can be consumed by microbes before reaching water. Methane can seep upward through sediments, but it often meets an unseen biological checkpoint. In many places, microbes intercept it and use it as an energy source, converting methane into other forms before it can escape into the ocean. This microbial filter can be so effective that a strong methane source underground becomes only a faint signal in the water above. The reactions involved can reshape local chemistry, changing acidity and influencing what minerals form in the sediment. This matters because methane is a powerful greenhouse gas, and the deep seabed can act like a buffer that reduces how much is released. It also matters for life, because where methane is being processed, a whole community can form around the energy flow, even without heat. The captivating part is the idea of prevention through biology. The seafloor does not only leak gases. In many places, it also hosts the organisms that quietly keep those gases in check. Oxygen minimum zones above can shape which animals survive on the bottom. The seafloor does not live in isolation from the water above it. When an oxygen minimum zone develops, bottom waters can carry less oxygen to the seabed, and that reshapes the community that can endure there. Some animals tolerate low oxygen by slowing activity, expanding breathing surfaces, or relying on behaviors that reduce demand. Others cannot cope and vanish from those areas, leaving gaps that change how the ecosystem functions. The boundary can shift over time, which means a site that once supported diverse life may become far more selective, or later recover if conditions improve. In coastal regions, this can also interact with nutrient runoff and changing circulation, creating stressful conditions for bottom dwellers. The story is compelling because it shows how the deep can be controlled by the invisible makeup of water. A small change in oxygen can decide whether the seabed is bustling or sparse, and it can redraw the map of survival without moving a single rock. The deep-sea food web depends on tiny choices made by microbes. Before most deep-sea animals can benefit from sinking organic matter, microbes get the first turn. They break down complex material into simpler compounds, decide which molecules remain available, and shape the chemistry that other organisms experience. In sediments, microbes control how fast oxygen is used, how nutrients are recycled, and whether certain reactions dominate in deeper layers. That microbial activity influences which small animals can live in the mud, which then influences the larger animals that feed on them. It is a chain built on microscopic decisions, repeated everywhere across the seafloor. This also means the deep sea can respond to changes at the surface in subtle ways. A shift in what sinks down changes what microbes can process, and that changes what energy is passed along. The wonder is that the largest habitat on Earth runs on the smallest managers. Microbes are not background characters down there. They are the ones setting the menu. Many seafloor animals use slow metabolism to endure long periods without meals. On the deep seabed, food can arrive unpredictably, and that uncertainty shapes how bodies are built. Many animals conserve energy by running on a slower internal pace, which means they can wait longer between meals without failing. Movements can be deliberate, growth can be gradual, and reproduction can be timed to rare opportunities. Some species store energy when they can, then rely on those reserves through lean stretches. Others are built to exploit sudden windfalls, like a fallen carcass or a concentrated patch of organic material, then return to waiting. This strategy is not laziness. It is precision, tuned to an environment where every calorie matters. The deep sea rewards endurance. A fast lifestyle would burn through reserves too quickly, and a missed meal could be fatal. So many seafloor animals live like patient accountants, spending carefully, surviving quietly, and persisting through long gaps until the next chance arrives. Seafloor spreading helped scientists prove that continents move. For a long time, continental drift sounded like a clever story with too few receipts. Then the ocean floor began to supply the missing evidence. Researchers realized the seafloor is not ancient and static. It is continually created at mid-ocean ridges, then carried outward, which means the ocean basins behave like moving belts. That simple idea suddenly made many puzzles fit. Why do matching rock types and fossils appear on far-separated shores? Why do earthquake and volcano zones trace such clear arcs and lines? Why does the ocean crust tend to be youngest near ridges and older farther away? Seafloor spreading turned drift into a measurable process with rates that could be estimated and tested. It also moved geology from argument to prediction. If plates move, then past coastlines can be reconstructed, and future motion can be forecast. The ocean floor gave motion a mechanism, and the world map stopped being fixed. The pattern of magnetic stripes matches on both sides of ridges like twins. When ships towed magnetometers across the open ocean, they found long bands where the magnetic signal rose and fell in a repeating way. The striking detail was symmetry. On one side of a ridge crest, the pattern could be mirrored on the other side, as if the seafloor had been printed in pairs. That matching offered a powerful test, because symmetry is hard to fake. It suggested the seafloor was being produced at the ridge, and then carried away on both sides at similar rates. Scientists used the spacing of the bands to estimate how quickly the crust moved, and they compared different oceans to see how spreading rates varied. This twin-like pattern became a map you could read, even without seeing the rocks directly. It helped turn a hidden process into something trackable, and it gave plate motion a fingerprint that could be traced across whole basins with nothing more than careful surveying. Mid-ocean ridges shape ocean circulation by steering deep currents around basins. Deep currents do not flow through empty space. They encounter undersea mountains, saddles, and long barriers that redirect them like walls in a maze. Mid-ocean ridges are among the largest of those barriers, stretching for great distances and forcing water to find gaps, passes, and fracture-zone pathways. That steering affects where cold, dense water can travel, how it mixes, and how long it lingers in a basin before escaping. The consequences can reach far beyond the ridge itself, because circulation influences how nutrients are distributed and how heat is stored in the ocean interior. In some places, a ridge can act like a gate that limits exchange between basins, while in others it funnels flow through narrow corridors that intensify currents. The seafloor becomes part of the ocean's plumbing. It quietly guides the routes that water takes around the planet, shaping the background circulation that the surface world depends on. Seamount chains can mark hotspot tracks, recording plate motion histories. Sometimes the seafloor shows you a trail, like breadcrumbs leading into the past. A chain of seamounts can form when a plate moves over a long-lived source of magma, deep within the mantle. Each volcano forms, then the plate carries it away, and a new one forms in its place. Over time, a line of progressively older mountains is left behind. By dating rocks from different points along the chain, scientists can estimate how fast the plate moved and whether its direction changed. Bends in a chain can hint at a shift in plate motion, which turns the seafloor into a record of tectonic choreography. These tracks also help explain why some regions host clustered volcanoes, while others do not. The magic is that motion is preserved in shape. You can look at a map and see not just mountains, but a history of travel written across the deep. Hawaii's volcanic story continues underwater, with huge flanks hidden below waves. When people picture Hawaiian volcanoes, they often picture the islands above sea level. Yet most of the volcanic structure is underwater, with enormous slopes extending down into the deep. Those hidden flanks record long phases of growth, collapse, and rebuilding that you would never guess from the shoreline alone. Underwater mapping reveals ridges, terraces, and deposits that show how lava and debris spread outward, building the base of the volcano far beyond the visible coast. Submarine landslides have also played a role in shaping the island's underwater architecture, leaving signatures on the seafloor that speak to past instability. Studying the underwater portion helps scientists understand how ocean island volcanoes evolve as whole systems, not just as scenic peaks. It is a reminder that an island is only the tip of a much larger mountain, and that the main body of the story is written in darkness beneath the waves. Some underwater landslides can generate tsunamis without any major earthquake. It is possible for the seafloor to shift enough to move the ocean, even when there is no huge quake to announce it. If a mass of sediment on a steep slope becomes unstable, it can collapse and surge downslope, displacing water as it goes. The wave that results can travel outward as a tsunami, and the cause may be hard to recognize in the moment, because the usual warning, strong shaking, might be absent. Triggers can include smaller quakes, rapid sediment loading, or changes that weaken layers over time until failure happens. Afterward, the seabed can show a scar where material broke away and a debris field where it came to rest. This is one reason scientists study continental slopes so carefully, and why tsunami hazard assessments consider more than earthquakes alone. The seafloor has its own ways of suddenly changing shape, and water responds immediately. Subduction can drag sediment down, or scrape them off into accretionary wedges. As an oceanic plate approaches a trench, it carries a blanket of sediments that have accumulated over time. What happens next depends on the details of the boundary. In some places, much of that sediment is pulled downward with the plate, disappearing into the deep earth. In other places, the sediments are scraped off and piled against the edge of the overriding plate, forming a thick, deformed mass called an accretionary wedge. These wedges can be folded, faulted, and fractured, and they can grow as more material arrives, like a slow-motion bulldozer pushing a mound forward. Over long spans, parts of these wedges can rise and become land, which means today's coastline geology can include material that started as ocean floor mud. This process also influences earthquakes, because the nature of sediments affects friction and fluid pressure along the boundary. A trench is not only a meeting of plates, it is also a sorting process for the seafloor's accumulated layers. Mud volcanoes can erupt cold slurry, driven by gas pressure underground. Not all volcanoes involve heat and molten rock. Some are powered by pressure and sediments. Gas and fluids build up below the seabed, and when they find a pathway upward, they can carry a mixture of mud, water, and fragments of rock to the surface. The result can be a cone or mound, with flows that ooze outward like thick paste. These eruptions can happen on continental margins and in tectonically active regions, and they can release methane and other gases along the way. The landscapes they create are strange, because they resemble volcanic landforms, yet remain cool to the touch in temperature terms. Mud volcanoes also bring buried materials to the surface, which gives scientists clues about deeper layers without drilling. They can create specialized habitats too, because the chemistry of the expelled fluids can support distinct microbial communities. It is geology using pressure rather than fire, and it reshapes the seabed in a way that feels both familiar and surprising. Gas bubbles can stream from seeps for years, mapping hidden faults below. Sometimes the sea floor reveals its cracks by exhaling. At seep sites, bubbles can rise in steady streams, marking where gas is escaping from sediments below. These bubble plumes are not just curiosities. They can act like indicators of underground pathways, because faults and fractures often provide the routes that fluids use to move upward. By mapping where bubbles emerge and how the seep field changes over time, researchers can infer the structure of hidden fault systems and the way pressure is moving through sediment layers. Acoustic instruments can detect the bubbles in the water column, which means seeps can be surveyed over wide areas without direct visual contact. The persistence is part of the fascination. A seep can remain active for years, quietly tracing a line that tells you where the subsurface is permeable, where gas is stored, and where the seafloor is connected to deeper reservoirs. The ocean floor in these places becomes readable through its own slow breathing. Certain deep-sea sediments host natural antibiotics made by competing microbes. In seafloor sediments, microbes live crowded together in a world where space and energy can be limited. Competition can be intense, and one way microbes compete is by making chemicals that inhibit their neighbors. Some of those compounds function as natural antibiotics, and they can shape which species dominate a patch of mud. This chemical rivalry has scientific value because it expands the library of molecules that biology can produce, and it offers hints for new treatments when resistance undermines existing drugs. The deep sea is especially intriguing because its conditions are stable and unusual, which can lead to biochemical solutions that differ from those on land. Studying these molecules takes careful sampling and cautious interpretation, since contaminants can mislead results. Yet the core idea remains compelling. The seabed is not only a graveyard of particles. It is an active arena of microscopic strategy, where chemical inventions help determine who survives, and where those inventions may one day matter to human health. The seafloor holds hydrothermal minerals that once inspired theories of life's origin. Some scientists look at hydrothermal settings and see more than chemistry and heat. They see a natural laboratory that can bring simple ingredients together, concentrate them, and keep them reacting. Porous mineral structures can create tiny compartments with different conditions only millimeters apart. One pocket can be more acidic, another more alkaline, which sets up natural gradients that resemble the energy differences living cells use today. Certain minerals can also act like catalysts, helping reactions happen more easily than they would in open water. That has inspired ideas that early life may have begun as networks of reactions, guided by rock surfaces and fueled by chemical disequilibrium. Over time, those reaction networks could have become more organized, eventually finding ways to build membranes and carry information. It is not a proven origin story, but it is a compelling one. It suggests that Earth's chemistry may have offered stepping stones toward biology, right on the ocean floor. Some vents emit faint sounds, created by boiling fluids and cracking rocks. Hydrothermal systems do not only release hot water and minerals, they can also produce sound, a low, subtle soundtrack shaped by physics. Fluids rushing through narrow channels can generate vibrations, and sudden changes in pressure can trigger popping or hissing as gases separate from the liquid. In some places, the heat is high enough that fluids can undergo phase changes under pressure, and the turbulence can add its own acoustic signature. Rock plays a role too. As the crust heats and cools, it expands and contracts, and fractures can open or slip, producing tiny crack sounds that instruments can catch. When researchers deploy hydrophones and seafloor sensors, they can sometimes detect these signals and use them to infer changes in flow. A vent field can become something you can listen to, not just map. It is a reminder that the deep ocean is full of activity that does not need light to announce itself. The abyss has seasons too, when surface blooms send extra food downward. Even in the deep, the year can have a rhythm. When surface waters bloom with plankton, more organic material can sink toward the bottom in a delayed pulse. Weeks later, or sometimes longer, the abyss receives that delivery, and the response can be measurable. Sediment traps can catch a sudden increase in falling particles. Seafloor cameras can show animals gathering, feeding, and becoming more active, as if a sparse landscape just received a shipment. In some places, the seabed community can shift its behavior in step with those pulses, because the deep depends on what the upper ocean produces. The timing and strength vary by region, and that variation becomes part of the mystery scientist's study. It is fascinating to realize that the deepest planes are not cut off from the sky. They are linked to surface seasons by gravity and sinking carbon, arriving as a delayed signal from far above. Deep-sea fish often have huge mouths because meals are unpredictable. In the deep ocean, finding food can be a rare event, so some fish are built to never waste an opportunity. A large mouth, expandable jaws, and a stretchy stomach let a fish capture prey that might be almost as big as it is. That sounds exaggerated until you see the anatomy. Hinges and ligaments are arranged for opening wide, and teeth can be angled to keep prey from slipping away in the dark. For some species, the goal is not speed, it is capacity. If you only encounter a decent meal now and then, it makes sense to be prepared for whatever passes by. Some deep fish also use light to lure prey closer, then snap forward with a sudden strike. The mouth becomes a survival strategy shaped by scarcity. It is a design built for a world where you cannot count on the next bite, so you plan for the biggest one you can manage. Many trench animals accumulate unusual chemicals that stabilize proteins under pressure. At extreme depth, pressure can subtly distort the shape of proteins, which can disrupt the reactions that keep cells alive. Some trench animals counter this by building up molecules known as piezolites, which help proteins hold their working form. One well-known example is TMA, a compound found in many marine animals that can increase with depth, acting like biochemical support. This chemistry is not free. Managing these molecules affects osmotic balance, energy use, and how cells handle salts and water. So the adaptations have to be tuned carefully, not just maximized. Different groups solve the problem in different ways, which is why trenches can host a diverse set of pressure strategies, even among animals that look similar on camera. The deeper you go, the more you see that survival is not only about strong bodies. It is about molecular engineering. Life in trenches is chemistry that refuses to fold the wrong way. Seafloor mapping uses sound because radio waves fade quickly in seawater. If you want to see the bottom of the ocean, you mostly cannot use light, and you cannot rely on radio signals the way you do in air. Seawater absorbs radio quickly, especially at the frequencies that would carry detailed information. Sound, however, travels far, and it can be measured with precision. A ship sends out a pulse, then listens for the echo that returns from the seabed. The time it takes, combined with the known speed of sound in water, gives a depth estimate. The tricky part is that sound speed changes with temperature, salinity, and pressure. So oceanographers collect profiles of the water column to correct their calculations. Without those corrections, a map can warp. When it is done well, sonar turns the ocean into a measurable space, converting echoes into mountains, valleys, and plains. It is like drawing a landscape by listening, where every ping is a question and every return is an answer. Multi-beam sonar can reveal ship-sized features, even miles beneath the surface. Older sonar methods often measured one depth point at a time, like tapping the ocean with a single cane. Multi-beam sonar changed that by sending out a fan of sound beams across a wide swath beneath the ship. Each beam returns an echo from a slightly different angle, which lets scientists build a detailed cross-section of the seafloor as the ship moves forward. Stitch those swaths together, and you get a textured map with ridges, scarps, lava flows, and landslide debris fields. Multi-beam systems also measure backscatter, which gives clues about how hard or soft the seabed might be. That can hint at sand, mud, bare rock, or rough lava, even before anyone sent a camera down. The result can be startlingly vivid. A feature the size of a ship can stand out clearly, even under miles of water, because the ocean itself becomes a medium for measurement. New seafloor can record Earth's past ocean chemistry in altered basalts. Fresh basalt forms at ridges, but it does not stay chemically untouched. Seawater moves into cracks and pores, reacts with minerals, and leaves behind a record of that interaction. Over time, the basalt can develop veins, secondary minerals, and altered zones that incorporate elements from seawater. Those changes can preserve chemical clues about the water that circulated through the crust, including signals in isotopes that scientists use like fingerprints. In some cases, the altered rock can even trap carbon in mineral form, locking it into the crust. Studying these basalts helps researchers understand how the ocean and solid Earth exchange material, and how that exchange may have differed in the past. It is a kind of memory written into stone. A lava flow begins as molten rock. Then the ocean edits it, imprinting chemistry into its structure. Long after the water has moved on, the basalt can still carry that history, waiting in the crust like a sealed letter. Many ocean floor mysteries remain, because less has been explored than the moon. It is strange, but true in spirit. We have better global images of the moon's surface than we have direct views of most of the deep sea floor. Water blocks light, pressures crush equipment, and missions are expensive and slow. A vehicle that works perfectly at the surface may fail after hours in the deep, and communication is limited, so autonomy matters. Even when sonar maps are excellent, they are not the same as seeing. A smooth patch on a map might hide a field of nodules. A ridge might conceal cracks that host life. Each expedition covers a thin track across an enormous world, and large areas remain known only in broad outline. That is why new discoveries still happen in places that feel close to home. The mystery is not because the seafloor is empty. It is because it is vast, dark, and hard to reach, and we are still learning how to explore it well. Every step of seafloor science reminds us Earth is still an active planet. The ocean floor is not a finished foundation. It is where the planet keeps working. New crust forms, old crust sinks, faults slip, and sediments move in sudden pulses. Water circulates through rock and comes back changed. Life adapts to chemical energy, pressure, and scarcity in ways that expand what we thought biology could do. When scientists lower instruments into the deep, they are not just collecting data. They are listening to a planet that is still building and recycling its surface. That perspective can change how you think about land, too, because the same forces that shape trenches and ridges also influence coastlines, earthquakes, and volcanoes. The deep sea floor makes Earth feel less like a static globe and more like a living system, with energy moving through rock, water, and time. The more we learn, the clearer it becomes that the most familiar planet in our lives is also one of the most dynamic, especially in the places we rarely see. As we come to the end of our descent, take a moment to feel the scale of where we have been. We traveled across plains wider than continents, along mountain chains that circle the globe, and down into trenches deeper than the tallest peaks are high. We followed newborn crust as it formed in fire, and we traced ancient sediments that remember climates long past. We drifted past chimneys that breathe minerals into the sea, and quiet plains where life survives on the faintest fall of food. The ocean floor is not an empty darkness. It is a shifting landscape of ridges, valleys, hidden currents, slow-growing corals, patient microbes, and restless plates. It shapes continents, stores carbon, carries cables, and shelters creatures built for pressure and night. Beneath the waves, the planet is still at work, building, recycling, and recording its own history in rock and mud. Now, let that vastness soften in your mind. Picture the seafloor settling into stillness. The currents ease. The sediment drifts downward in a slow, steady fall. The ridges and trenches rest beneath miles of quiet water. If you enjoyed this journey across the deep, you might like to explore the next one waiting on your screen. And if these explorations help you unwind, consider subscribing or sharing the channel so more curious minds can drift down with us. For now, allow your breathing to slow. Let your thoughts move like distant currents, unhurried and calm. The ocean floor will continue its ancient work without you. You can simply rest. Sleep well, and good night.